Good afternoon, ladies and gentlemen. Welcome to the second episode of the webinar series being hosted by Mageba, getting encouragement by the success of our last webinar on structural health monitoring. We are pleased to present today the topic addressing structural bearings, which I am sure would be of interest to any practicing bridge engineer. My name is Chinmay Ghosh, and once again I am privileged to be your host today. As you know, the topic of today's webinar is latest development on structural bearings, which will be presented by my colleagues, Daniel Begle from Mageba, Switzerland. Yes, hi Daniel. And Meghna Dayananda from Mageba, India. Hi Meghna. Okay. Next slide, please. Let me briefly introduce the speakers. Yes, Daniel, as you know, is an ABET mechanical engineer. He is a specialist in structural bearings with experience in robo-smart bearings, that is bearings equipped with sensors to measure the loads and forces and movement of bearing, to track the movement, record everything. He has more than 10 years experience in this particular field, whereas Meghna is a Master of Science in Civil Engineering from Dresden University, Germany. She is with Mageba for over the last 7 years. Is a senior project manager looking after the market in South India as well as Sri Lanka. Okay, so here is the content of today's presentation. The subject covers structural bearings. This will target to address the basic information on structural bearings, the basic design concept, design philosophies, and construction methods of different types of bearings which are in vogue. There are some bearings which are preferred over the other in particular application. So how different bearings are used in different applications, we'll know those topics. Also, we'll address some case studies with particular application of some of the bearings that are being in use. There are some case studies, 1 to 3 case studies here today will be presented by Meghna. So the first part of the topic about the types of bearing and the basic philosophy, that will be presented by Daniel, and the next part about the case studies will be presented by Meghna. With that introduction, I hand over to Daniel, who will take you through the next part.
Thank you very much, Chinmay. Yeah, so it is my pleasure here to give you an overview and introduction to bridge bearings. As maybe many of you know, but certainly that bridge bearings are an extremely important component on the bridge. I like to think of them as the knee of the bridge, connecting the lower parts to the upper parts, and just like our knees, quite an important piece. So next slide, please. And yep, generally speaking, there are the functionality of the bearings involve the transfer of vertical loads primarily, horizontal loads secondarily or sometimes primarily, and then of course all the movements and rotations necessary between lower and upper connection surfaces. And of course bearings can also be capable of things like seismic isolation or the restraining of vertical uplifts. As you may be able to guess, these are certainly wear components, so maintenance and inspection is also a crucial part of having bearings on parts of the bridge. And just a note that some of these special functions can reduce the requirement for other specialist pieces, such as tie downs on a given part of the bridge. And just to give you an idea of the range of possibilities here, bearings can be very small. As you can see here, something like this could be lifted by a single person, something like 30 kilos. A bearing of this type could have a capacity of something like 200 kilonewtons or so. So significant capacity even for their size, but just to give you an idea of kind of the low end of the spectrum. And then on the other side, bearings can be very, very large. Something like this taking 1,000 tons and being a couple of meters in diameter. So bearings can certainly also get very large. In terms of classification of bearing groups, we like to sort of think of these in terms of the way in which they will distribute movements or rotations. So at the top, we've got movement or rotation that would be conducted via deformation. So you can see a little diagram of shear or complete compression on the upper left side, and then the upper right, we have something like differential compression where we can accommodate rotation. And then the next type would be using a sliding surface, something like PTFE, sliding both for planar translation, but also rotation with a curved sliding surface. And then more of a direct or point contact concept at the bottom you can see for something that would roll or components that rock against one another. And we'll look at this in a little more detail coming up. And yep, in terms of the classification, so we refer to bearings typically in three major groups. That would be fixed, free, and guided. And just as the names say, a fixed bearing, of course, cannot move, but can transfer, cannot move planarly. It can rotate, of course, but typically would not move in the XY, but would transfer forces in those directions. A free bearing is just the opposite. It can move in the XY plane freely, but does not transfer significant forces. There are some interesting little exceptions here that I'll talk about a little bit as well, but typically that's what a free bearing is. And then guided bearings are just a mixture of the two. Typically in one of the two directions, X or Y, they would transfer force, and then in the opposite, they would allow movement. So just with that pretty simple overview there, we'll look at some specific types of bearings next. So yeah, we typically classify bearings based on capacity, and from left to right, we have the fully metallic bearings, rocker and roller bearings that use metal to metal contact for all of the transfers and rotations. Elastomeric in the middle. These can be planar reinforced, of course. And then HLMR is sort of an umbrella group with a few different formats there that stands for high load, multi-rotational. And these are pot to disc and spherical that we'll look at. But an important note I want to make on this slide is that it's actually crucial for understanding here that these are not worst to best bearings. It's all based on application. There are actually certain ways in which, just as an example, elastomeric bearings can be superior to even the latest high-tech bearings given certain applications. Just as an example, an elastomeric bearing functions a bit like a spring, and none of the other bearings would do that. So in cases where there's movement as well as some restraint required simultaneously, there's really nothing but an elastomeric bearing that could do that. So really important to understand that these aren't lesser capable bearings on the left and more capable on the right, but really just application based. So rocker and roller bearings, typically completely made out of steel. Functionally speaking, it might be easy to see on the upper bearing, it's able to rotate about the curved axis there, but not about the other one. So typically a rocker bearing would be single axis of rotation, and then movement via some sort of sliding. Roller bearings, the orange ones at the bottom, are a cylinder on a plane, and so of course this can can translate via pretty straightforward rolling, and these are suitable for high rotation or high movement type of applications, and it can do those quite easily. In terms of their limitations, as you can guess, steel on steel is relatively high friction compared to other options. So in certain instances, this may not be favorable, but like I said, it's really application based. There are times where a rocker bearing really does outperform most other bearings. It just really depends on what the situation is. One of the limitations could be space, for example, because a roller bearing is quite tall. You need the entire cylinder, so this can be pretty tall. And then the concrete would have to be quite strong. You can imagine when you have this point of contact, like in the lower picture, you need quite some distance to distribute that load, or you need a very strong concrete. So, yep, like I said, just application based. Elastomeric bearings. My personal maybe favorite bearing comes in a couple of variations, natural and chloroprene rubber. All of the movements and rotations are via some kind of deformation of the material. And so, as you can imagine, like a spring, it can flex in all different directions. And typically we would think of these as suitable for small to medium loads and relatively small movements. A lot of designs are possible, but those are the general groups. In terms of their advantages and challenges, for small loads, these often have a very compact size, a low cost, typically speaking. Maintenance can be extremely low, especially when designed inside of their parameter umbrella. They can really have a extremely low maintenance and very, very long design life is common with elastomeric bearings. As you can imagine, the corrosion issues will typically be very low because all of the metal oxidizing elements are completely contained inside of some kind of elastomeric casing. They have damping properties, which, like I said, is not common to any of the other bearing types. They resist the load while simultaneously taking a movement. So this can be a favorable attribute. And then there are instances where uplift is possible in a simpler fashion than some other designs. So again, it's a bit of a special situation, but just to illustrate the idea that really it's never a better or worse question, but rather what's best for the application. Of course, the cost effectivity is really based on whether or not these things become extremely large. Then you may want to move to other bearings, for example. Vulcanization, the process by which the bearing is constructed, can be difficult as the size increases. And then, if you need to add a sliding system to an elastomeric bearing, you're normally better to go with a different bearing. And then, if it needs to be fixed, this can also create some complexity. But generally speaking, elastomeric bearings are good for most applications. And then we look at a whole category together, the high load multi-rotational. There are 3 general groups thereof: pot bearings, disc bearings, and spherical bearings. And you might be able to tell that the lower and upper parts of all these bearings are pretty similar. Typically a upper plate, a lower plate, and then some transfer. And the cores are the real difference, the centerpieces. And we'll describe those in some more detail, but just to kind of give you a background where these come from, the pot bearings were developed in Europe quite a long time ago, and they're widely used in Europe. Disc bearings they were developed in the US. They're used everywhere that I know of almost. And then spherical bearings are another European bearing, but both the pot and the spherical bearings are widely used, I would say. So just an overview of the structure of a pot bearing. So like I said, the slide plate is common to all 3. Underneath that, we have a PTFE or other sliding surface. Moving down, we have a piston, which integrates into the pot for both transfer and to contain the elastomer. The elastomer acts sort of as a liquid. There's a liquefaction effect under a lot of pressure, and this is what gives the smooth rotation of a pod bearing. And they're suitable for medium to high loads and moderate to high rotation, something around 40 millirad or so. And then movement is, yeah, of course, there could be a lot of movement because it just depends on the size of the sliding plate versus the piston, and those can be as big as you like. Just an example of the assembly of a pod bearing there. That's the piston being inserted into the pod with some transportation rods. You can see 3 of them there on the outside that hold it together to move around. This is an example of a movable pod bearing. It's not super easy to see, but that outside rectangular piece is the guide, and then there's a little silver kind of component you can see just to the right side of the guide, and that is a sliding material. And so the sliding will happen between the part labeled guide and the inner piston portion. In terms of the overview of them, pod bearings, they're ideal for cases with horizontal vertical load ratio that's favorable, not too high on the horizontal load, for example. Of course, because this elastomer is confined, you have smaller vertical deformations. Sometimes that's important, sometimes it isn't, it all depends. There's a small restoring moment. Like I said, the elastomer basically acts in a sort of a liquefaction state, so there's really not a lot of resistance to rotation here. Of course, there would be an issue of metal-to-metal contact under rotation because the pod and the piston can be quite close together. This is a design parameter, but it is a possibility. And then but what is sort of impossible is to inspect the elastomer. It's contained completely between the piston and pod, so you can't see it unless it comes out. So under normal conditions, it would not be visible for inspection. And disc bearings, like I said, similar, very top and very bottom to a pod bearing, but in the middle is the difference. Actually similar with the sliding disc here, PTFE. The way that the vertical loads are transferred are through this PU disc component, and it's harder than the elastomer used in the pot by a significant amount because it's uncontained, so it has to transfer all the force itself. And so these are suitable for similar loads to pot bearings and similar rotations, though rotations are arguably a little bit less than would be a pot bearing because the disc has to absorb all of it. But yeah, this again, based on the design and the application, this can be as much as a pot bearing. And just to show you what the assembly might look like there, pin in the middle, the disc simply sits there in the space that's sort of the lighter color gray. That's where it would be installed. And this is a sliding version of a disc bearing. So, and this actually is a good demonstration of another kind of sliding material possibility, ultra high molecular weight polyethylene at the top, and a sliding strip out of the same material. We'll go into a little detail about what that is exactly, but just that there are material options, and this is a sliding version of a disc bearing. And yep, just another kind of illustration of a disc bearing all put together there. In this case, the way that it's configured would be such that it would be bolted or anchored via dowels to an upper and a lower surface. And in this configuration, it's hard to say, but it could be, concrete above or below, or steel. And just an example of some more options for angled upper-lower relationships. Here we have a beveled plate, so this allows there to be a non-planar relationship between the upper and the lower connection. And just an example, again, here of some transport fixation that holds the bearings together for transport. And yep, and the overview here. disc bearings are quite simple and therefore cost effective in terms of construction. They're easier to inspect because the disc is visible, so you can see the crucial part during inspection. They're resilient to the environment because, again, this disc is a polymer that is designed specifically for that. And then typically they have quite a low height. In terms of some limitations, like I said, rotations can be a challenge. All depends on the application. And then the disc itself actually resists rotation, for example. So this could be a situation where it's important in the design stage to ensure that this resistance to rotation, let's say, is accounted for. And then, yep, in certain high horizontal, low vertical load applications, it can be less economical than other options. And yep, finally, spherical bearings. So what makes these interesting is that none of the elements of them compress in the way that basically all of the other bearings do. So all of the rotation and transfer is done via curvature. So that makes them suitable for a higher load range as well as higher rotation ranges. And they're ideal for situations where there's low vertical and high horizontal loads in combination. That's something relatively difficult to deal with in other ways sometimes. And just to kind of illustrate the important design tenet that allows this transfer of these high horizontal loads, you can see in the upper picture that the load is being transferred into the upper culotte, let's call it, the top curved of the two curved pieces. And then that has to transfer into the lower part, but of course you can imagine with enough force you would have some slippage between those two parts. And the design that we utilize simply bypasses that problem. So with a spherical bearing designed as the lower picture, we bypass the issue where you would have separation of those sliding surfaces. And just a picture of that basic concept. Guides that transfer directly to the lower part and bypass the rotation element. And yep, as I mentioned, the spherical bearings do not have or have very little, let's say, there's always going to be some deformation, but very little deformation under a vertical load. And so this differentiates it from some other bearings, but like I said, it's important that this is not seen as superior, but rather based on the application, maybe you do want some of this deformation, or maybe the deformation is coordinated based on the scenario. So it's just sphericals allow another option, basically. And just to show a sort of a special design that allows a frequent uplift kind of scenario, this is a spherical bearing, but there are several, let's say, spherical parts that are all coordinated to allow for a pre-stressed bearing makeup and some more frequent uplift capacity, but just an illustration of what's possible. And then another kind of specialized design, Magana will get into much more interesting things here in just a minute, but just to kind of demonstrate that within not only the spherical and cylindrical type bearings, but in all types, there can be custom designs or special designs. But this is a cylindrical example. So spherical has basically two radii of curvature, and a cylindrical is a single radius. It's not unlike the rocker bearing, but both surfaces are in contact. And this particular application is to be able to also transfer moments about the vertical axis. That's very unusual for most bearing applications, but this just is a demonstration of how some of the cylindrical design concepts can transfer this moment. And don't worry if I don't go over every detail on the slides. There is a handout, like Chinmoy said, and you'll be able to look in greater detail at some of these slides. So, yep, just we saw this example before, but just to sort of illustrate these high-grade sliding materials, that ultra-high molecular weight polyethylene can really transfer a lot of load, 3 Eiffel Towers worth, let's say, or something like 2,500 tons. And we'll look a little bit more at the specifics of the sliding material in just a minute. And yep, so the question is, why do we even bother with another kind of sliding material when PTFE is so common? And that's true, PTFE is common, and just like with the bearings, it has its applications, and there are reasons certainly to use PTFE in certain cases. Yeah, there's a few details here about it, but we'll get into a comparison on the next slide here. So with the sliding materials, we might actually be looking at something that is sort of a superior situation, but again, everything has its applications. But just to show you the difference between the UHMWPE material and the PTFE, friction coefficients at given temperatures were 0.5% lower at 20 degrees centigrade and entire percent at -34. So this sounds relatively small. 0.5% is typically not considered a lot, but it's quite significant when the total is 2%. I mean, it's it's 25 or 30 depending on which way you're moving the calculation, but it's a significant amount. The design pressure is even more dramatically different. Let's say it's almost 3 times. We typically design with, say, double, but you can imagine that does open up some more avenues for design. And finally, the resistance to wear, which on the face sometimes does not seem as important, but it can be very crucial in terms of the life of the bearing. And this is again around double. So we really do like to implement this UHWMPE when we can. And yep, just a summary of the spherical bearings. So they're ideal for very large rotations. There would be instances where a given rotation would be hard to do without a spherical design. So this is a particular application that's good for that. They do provide quite a compact load, or a compact format, but this is important, again, to understand that you still have to distribute this into concrete. So it's a very application-based. And with frequent uplift, these are the go-to design for us. And then, of course, like I said, these large horizontal relationships are also possible. Some limitations are that they can be taller than comparable designs, so application there. Like I said, the adjacent concrete must be strong enough, and there are instances where if the bearing's relatively small, the rotation is large, it's really going to have sort of a prohibitive ratio of sizes. So these are definitely state-of-the-art bearings, but it's important to know that they are very, or all of the bearings are application-based, so one is not necessarily better than the other in any given case. So yep, I hope I gave you an introduction and a bit of an idea of our bearing distribution. I'm going to hand it off now to Magana, and she's going to get into the really fun stuff of the case studies.
Thank you, Daniel. Good afternoon, everybody. I will now take you through some of the latest developments in bridge bearings. Of course, we cannot cover all of them in this brief session, but let's try to understand some prime examples through a few case studies. With that, let us begin with case study 1, which is the deflection control at hinge point and balance cantilever construction. Firstly, we all know that balanced cantilever type of construction became very popular for long span bridges due to ease and economy of construction. As and how spans got longer, engineers started leaning towards bridges with continuous spans. But with continuous spans came the problem of structural indeterminacy. Back in the day, when computing power of computers was much lesser, one encountered a lot of problem while analyzing the structure itself, right? So engineers introduced a hinge point at the mid-span location to make the structure statically determinate while simultaneously enjoying the perks of the balanced cantilever construction, which was pretty intelligent. But there was one major pitfall that challenged all the above mentioned advantages, and that was to realize this idealized hinge point. So if you could see at the picture at the top right, an ideal hinge is located at midspan, and the behavior of the structure can be seen as to how the live load moves along the span. The influence line of the bending moment at A is symmetrical about the hinge. But this is not so true for, or in the case of the not so ideal hinge, as it can be seen in the next picture, right? We can clearly see that in case of a not so ideal hinge, when the load is moving from one side of the hinge point to another side of the hinge point, the segment or the deck ends are not going to be moving in unison, which will cause a lot of fatigue stress and eventually maybe even loss of pre-stress on the cantilevers. In the very initial attempt to address this problem, a metallic plunger type bearing was used. But fatigue-induced stress due to repeated hammering effect, caused the steel components to wear out in a very short time. This can be seen in the topmost photograph, and also the extent of the damage can be seen in the bottom right photograph, where the bolts are completely sheared off. These are not pictures which have been taken off the net. These are pictures, actual pictures from the Kalpi Bridge over River Yamuna in Uttar Pradesh. So how do we address this problem? To address these issues, in about 2012, a certain type of bearing was applied, which was called the central hinge bearing. A central hinge bearing essentially consists of a male part and a female part. One pod bearing is housed at the top of the bearing, top of the male part, and another one is housed at the bottom part. The female part is provided with a sliding arrangement against which the pod bearings are pre-compressed. This prevents development of stress because of load reversals. Although this addressed the issue of damages to bearing components due to fatigue-induced stress, there was no way of understanding how much preload was being applied or how to ensure that the bearings remained in pre-compression throughout their intended lifespan. This two-part problem was addressed simultaneously when the central hinge bearings were equipped with Mageba's latest technology, a lift control mechanism. A lift control mechanism was introduced to ensure that preload as required could be applied. Now we already know that the central hinge bearings house pod bearings at the top and bottom. And my colleague Daniel already mentioned that the elastomeric pad behaves like a semi-fluid under compression. In a lift control mechanism, a special fluid is infused into the pod cylinder during the assembly at the factory itself to apply the required preload. This operation can be done 2 or more times during the entire service life of the bearing to ensure that it remains pre-compressed and also free from fatigue stress. To monitor the amount of pre-compression applied, piezo-resistive transducers were used. Such smart bearings were recently supplied to the bridge over River Brahmaputra at Tezpur in Assam. Here you can see a few real-time pictures of the central hinge bearing being assembled at the Mageba India's workshop and the ones installed at site. Now, another way of realizing this ideal hinge was and controlling the deflection at midspan was by providing a needle beam. This is also a popularly adopted solution these days. You may have guessed that this was the solution of choice even at the recently constructed third Narmada extradose bridge in the state of Gujarat. Here, a needle beam is inserted into the steel casing, which stretches from one side of the hinge point to the other. Between the steel casing and the needle beam, bearings are positioned. The location of the bearings are highlighted in blue, which you can, I'm sure, see on your screens right now. As you can see, these bearings are provided at 4 locations and are required to cater to frequent uplift in service condition. Generally, in these conditions, the height of the bearings are restricted to about 200 mm due to space restrictions or space constraints. In this slide, we can see that there is a schematic representation of the 4 bearing system. In this system, all the bearings resist uplift in service conditions, right? The uplift restraint bearings come with a hold down arrangement, which invariably increases the height of the bearings, and often we run the risk of not being able to fit these bearings within that restricted space. Further, the anchorage system in uplift bearings come with tension rods, which cannot be accommodated within the sort of inadequate concrete depth of the adjacent structure. So the issues are plenty. Of course, there are solutions when there are challenging issues, and to address this issue, a 8 bearing system was devised. In an 8 bearing system, things are much simpler. There is no uplift resistant bearing required. All bearings are in compression, and the most suitable type of bearing for this application generally is disc bearings, which was discussed in great detail by my colleague Daniel. Disc bearings transfer the horizontal forces through essential shear pain, as you already know, and the polyurethane disc transfers the vertical load while also accommodating the rotations. In this case, there was also no need of providing any tension anchorage system, as you can see in this picture. This is the photograph of the rest-on disc bearings that were supplied to the third Narmada Bridge project being assembled at our workshop in India. And another shining example of this application is the second Vivekananda Bridge over River Hooghly in Kolkata. Moving on to our next case study, which is about additional degrees of freedom. Now, we all know that there are 6 degrees of freedom, 3 translational and 3 rotational. Generally, bearings are designed to address about 4 of these. They take care of the rotations about the horizontal axis and the translation along the horizontal axis. But in some special cases, the bearings are required to take care of additional degrees of freedom. For instance, in this span, one can see that there are 4 joints, and joint 2, 3, and 4 are required to pivot about joint 1. The joints 2, 3, and 4 are also required to accommodate translation in the x-axis. Due to this, the bearings which are provided at all 4 joints will have to cater to another degree of freedom, which is the in-plan rotation. The bearings for Sky Bridge at ITC Colombo 1 in Sri Lanka had similar requirement. In this case, rest-on swivel bearings were proposed for joint 1, and rest-on swivel slider bearings were proposed for joints 2, 3, and 4. As you can see on the right side of the screen, the multi-level bearings cater to the additional degree of freedom by allowing in-plan rotation. And this is a photograph of the rest-on swivel slider bearing at the Mageba, India workshop. Of course, this was an example from the building sector. In the infrastructure space as well, such a challenge was recently encountered while designing bearings for the bridge number 8 over river Alaknanda at Lachmoli in Uttarakhand. Here, free pin guide bearing system was adopted. As most of you are aware, the metallic guide and pin bearings are placed under the diaphragm walls and not below the longitudinal girders. The pin and guide bearings here were required to rotate or accommodate rotations in the or about the vertical axis. To address this rather uncommon requirement, the metallic guide bearings provided had a special rotational element. As you may well know, metallic guide bearings do not transfer any vertical loads, and you can see a gap has also been provided in this bearing to ensure that there is no transfer of vertical loads. A central part is housed within the square metallic plate, and this entire arrangement enables the in-plane rotation. This is a picture of the huge metallic guide bearing, which was recently supplied to the Lachmoli project. Now let us move on to our last and final case study, which is the bearing choice for open web girder. This is a problem that occurs more often than not. So in this slide, we can see that pod bearing is provided at L0 location in bridge number 20 of the Jammu-Udhampur railway line. If you took a closer look, we can see that there is bending in the top plate of the pod bearing. This is due to lack of adequate stiffening at the bearing location itself. So let us try to understand this problem a little more. In a standard open web girder, the bottom cord consists of two parallel webs, which are at a certain distance apart and are connected by a thin gusset plate. And in the absence of additional stiffening at the bearing location, the parallel webs tend to impart two line loads over the top plate of the bearing. So if a conventional roller rocker bearing was used, then the loading pattern would not have been a problem. But in case a pod bearing or spherical bearing is used in the absence of adequate stiffening, this will result in localized bending, as you can see in the small picture which is inset at the top of the slide. So we developed a solution for this. It was the latest development in this regard, and it is popularly known as cylindrical bearings. They are the ideal solution for this problem. Cylindrical bearings have a form factor which is similar to that of the roller rocker bearings. And when this is combined with the advantages of the high performance sliding element, which Daniel spoke about earlier, we can address the issue very effectively. The load transfer pattern from the bottom cord of the web at the bottom cord through the bearing components is completely supported, unlike what happens in case of the pod or even a spherical bearing. In this slide, we can see the internal components of the cylindrical bearing. Displacement is taken care of by the sliding interface. The high performance sliding element is provided on top of the rocker plate. And there is a stainless steel sheet which is provided at the underside of the top plate. And in the bottom picture, one can see that a fully assembled cylindrical bearing has been assembled at one of the Mageba workshops. The Jammu-Udhampur rail line close to Girder was all set to open in 2013. This is a small story that I would like to bring to all of your notice. But upon inspection, it was found that there was a problem in the bearings, due to which the commissioning of the rail line itself was inevitably postponed. So after the bearing system was replaced with the cylindrical bearings, the section received the required safety clearance and was also commissioned for public use. I think this is one of a very important line for pilgrims who visit the Vaishno Devi temple as well. A similar solution was also provided to the Bhairav Bridge, or the second Bhairav Bridge in Bangladesh. Now, cylindrical bearings, like I said, it has many similar advantages to spherical bearings, and they can also be customized to provide uplift resistance too. Cylindrical bearings with uplift resistance were recently supplied to the bridge number 8 at Lachmoli over river Alaknanda in Uttarakhand state. We also discussed about this bridge a few slides ago. So these are some of the latest developments. I hope to have briefly introduced or brought them to all of you in a very concise, precise manner. With this, thank you for all your attention, and I request Mr. Chinmoy Ghosh to step in and take the webinar forward. Thank you all.
Thank you, Meghna. It was a nice discussion, concise discussion. So if you go to the next slide, I'll try to summarize the discussion that took place so far. Can you go to the next slide? Yes, next, yeah. So we discussed about many types of bearings. Other than the roller rocker bearings, we discussed elastomeric bearings, which are good for many load demands and have the benefit of extended service life. If a good quality elastomeric bearing is used, it can give you the longest life possible for any of the bearings because of its, the conspicuous absence of any corroding element in the bearing. Then there are these HMLR bearing, high load multi-rotation bearing, HLMR bearings, spot bearings, disc bearings, and spherical bearings. All of them are, the fundamental takeaway of this presentation was that there are many bearing options available to engineers, okay? And it all depends upon the application. One bearing which is good for one application might not be the best for the other application. For example, Meghna just showed you the example of a needle beam application where spherical bearing, more than the spherical bearing, disc bearing would be an ideal solution because of the nature of the application. So there are two bearings on top and bottom of the needle beam, which would be difficult for replacement if required if spherical bearing is used, because spherical bearing does not compresses at all. There is no compressible element. Whereas for a disc bearing and pot bearing, somehow a little bit of compression is available, which is beneficial for this application. So again, this non-compressibility of spherical bearing would be sometimes a very important factor which can be applied for the particular application. So fundamentally, there is no good bearing or bad bearing. Depending on the application, there would be one or the other that should be chosen. And for sliding material, of course, PTFE is the material of choice for sliding since the 1960s probably. And now you have this high grade UHMWP for higher load capacity requirement or high movement requirement where the sliding path, the total accommodated sliding path is higher than the normal application, then the high grade UHMWP could be a choice. Then again, sometimes for some applications you need a higher friction. For example, though we did not address that in this presentation, there are bearings like friction pendulum bearings where maybe you have requirement of a higher frictional material. Higher friction should not be less, rather a little high, but still sliding should take place. So there are many applications, and depending on that, many types of bearings and its components can be devised and applied. Okay, is there any other slide? I think there is one more. Yeah. Okay, so yeah, in the case study, there are a lot of custom solutions available. We have found that there are uplift conditions which can be restrained by some flow arrangement. And in one of Daniel's slide, you saw that there are, for frequent uplift cases, we have to design it in such a way that there is no, it is always in a pre-compressed state. There can be vertically installed bearing. And also this, we've learned about the bearings can now be equipped with a health monitoring solution, which would give us the real-time record of the loads and forces and movements that is happening in bearings. So it's not very expensive thing, as it may sound like that, but it's not so expensive for a large project and specialized application. We can always think of equipping the bearing with the special type of sensors, which would give you the real-time information on the bearings. Yeah. Next slide, please. Okay. So, any questions? Do you have any questions? As I told you before, that we can address questions from all the attendees. Let me check if there is any questions so far. Oh, interestingly, there is no questions this time. Oh, there is one question. I'll just address that. Mr. Sastry, PNSS Sastry writes, we'd like to know the life of elastomeric bearing. This is becoming the issue from durability point of view. Could you please let us know what would be the tentative life from your experience? It's a very good question, Mr. Sastry. Thank you for asking that. I tried to address that briefly if my co-speakers allow. So, yeah, life of an elastomeric bearing, as we know, is not affected by corrosion, not affected by fatigue, or not affected by wear and tear, because there are no such components which causes wear and tear or fatigue or corrosion. Life of elastomeric bearing only depends on the aging of the rubber. So since the steel laminates are encased within the rubber, so there is no possibility, there should not be any possibility of the corrosion of the internal steel laminates unless the rubber develops cracks, generates cracks. Why cracks can be developed? Because the rubber material ages over time. Aging takes place because of the oxidation of the polymer compound. During the vulcanization of rubber, long polymer chains are produced, which is cross-linked under heat and pressure. Those cross-linkages are broken when it is acted upon by oxygen available in the air, or it is more pronounced near the seaside, where there are more ozone in the atmosphere. The ozone being a very reactive chemical, as you know, there is a free oxygen molecule which reacts very quickly with any element it comes in contact with. So the aging of rubber takes place in a very big way in the coastal areas. So to prevent that, some anti-ozonants, anti-degradants are introduced during the mixing of the rubber. So the most important thing is the raw material of the rubber. If you look at our Indian code, Indian standard IS 83 part 2, there are specific grade of raw elastomer has been specified for protein rubber as well as for natural rubber, which should be of low crystallization grade. So low crystallization grade rubber are a little bit expensive than the other grades available. So the bearings, the raw material, if it is produced with the right quality of rubber and mixed with the right additional agents, admixtures, and produced in a way so that it does not degrade over time, elastomeric bearing can live as long as more than 100 years, 100 plus years. We had done some R&D in our own factory and found out the elastomeric bearing compound that they produce can live up to 114 years, at a average exposure temperature of 27 degrees centigrade. Of course, it depends on the exposure temperature. We can discuss it in greater detail in a different forum maybe, or if you can directly send us an email, we can send you some literature on this subject. Okay, there are further questions. So I took time because there was only one question. So for now, Mr. Ramaswamy is saying, what is the value of compression in terms of the elastomeric pad thickness in pot PTFE bearing? Okay, Daniel, would you like to address that? Or
yeah, absolutely, no problem at all. So factored compression is somewhere around 45 megapascals, give or take, on a pot bearing. We also have HP designs that are a specialized design. Whether or not we need a CE label, that pressure can go up. We have test data proving pot bearings above about 45 megapascals on the pad itself. You mentioned thickness, and the thickness is typically related to rotation capacity. So the pressure would be the same. Again, it's that the liquefaction effect. Because it's kind of behaves as a liquid, the pressure does not get affected by the height of the pad. There are other effects. I don't want to go into too much detail, but basically 45 MPa and the thickness is not very important.
oh, thank you, Daniel. There is one question from Mr. Vidyut Kumar Rai. He is asking whether, please provide us this wonderful PPT. Okay, Mr. Rai, you can find out the handout in the panel, where you can see handouts. We have already provided the PowerPoint, the PDF version of the PowerPoint presentation. You can download that from your system. Mr. Selvan P is writing a question for Meghna, disc bearings for spherical bearings for open web girder. Okay, Meghna, can you address that question? Meghna, you are muted, I guess.
I think you might be muted.
Sorry. So this is for open web girder, right?
Yep.
Yeah, if there is inadequate stiffening at the L0 location, please, we repeatedly suggest, please go for cylindrical bearings. They are a good solution. They are going to keep you very peaceful. But if you have adequate stiffening, say if it's a railway application, spherical bearings are also good. I mean, they're quite a good alternative if you have good enough stiffening at the bearing location, of course.
Absolutely. Okay, next question is from Gajanan Balu Chaudhary. Do pot bearings have limitations to be used in hot climates? Outflow of elastomer was observed in hot climates. Okay, I can address that question. I tell you that there is the outflow of elastomer is not dependent on the weather condition, Mr. Chaudhary. It's more of the the manufacturing tolerance that has been observed in the construction of the product. There is a very tight tolerance between the pot and piston, and there is a sealing ring all around the elastomeric pad. That the efficacy of the sealing ring and the control of the pot and piston interface is the most important factors in this case. So if those are controlled effectively, the temperature is not of a concern. Pot bearings can be used at a wide range of temperature application. So yes, to address your question, the outflow is not due to the hot climate. It is because of the inadequate or not uncontrolled tolerance between the pot and piston interface, and also the inadequacy of the sealing ring that has been used. We use nowadays the POM seal or polyoxymethylene seal, which is an improvement, much more improvement over the erstwhile blast sealing rings. So yes, so I hope that answers your question. There is the next question from Mr. Alok Bhomik. In India, we have problem of poor manufacture of elastomeric bearing. How do we deal with this issue? Question is addressed to Mr. Daniel. So Daniel, you answer this question. Poor manufacturing.
Okay. Yeah, no, this is exactly as Chinmoy said. The manufacturing of the elastomeric bearing and the material chosen are crucial. There can be a dramatic difference between a bearing manufactured in one way versus another, one material versus another. Exactly as Chinmoy said, it is very material related and degradation of the rubber. If a good rubber is chosen, good design parameters are chosen, the life should be great. Just an example, something we've recently started doing is increasing the distance between the outside of the elastomer and the steel shims on the inside. And what this allows is less chance that the steel shim will penetrate outside of the bearing. A simple example of what you say with manufacturing issues. You can design and manufacture to deal with those issues. So I would say the way you deal with the issues you're talking about, choose good materials, manufacture them intelligently, and design away from the problems that you see in the past.
Yes, that almost answered the question. Yes, also the manufacturing techniques. There are some steps that need to be taken during the manufacturing of the elastomeric bearing, which can be avoided, but that avoidance would mean cutting corners. So if those things can be avoided, elastomeric bearing, good quality elastomeric bearing produced. One thing that is important, since these bearings to be tested are subjected to repeated cyclic loading for vehicle movement, some fatigue testing has to be done for some millions of cycles, which is also specified in the Euro norm. And those bearings which comes with a CE mark actually has gone through such repetitive testing of fatigue, against fatigue, 2 million cycles or so. So a CE marking on an elastomeric bearing automatically gives you the confidence that it would last for a long time. Okay, quickly going to the next question. I think it's from Professor Devashish Bandyopadhyay. How do you monitor the performance of bridge bearing of an existing old bridge? Any test, etc.? Please put some light. Daniel, would you like to address that?
Yeah, absolutely. We have an entire webinar about that. But basically, there are many different monitoring technologies that we can mount to an existing bridge. They're completely non-invasive, so they simply install on the exterior of the bridge near a bearing, that sort of thing, and then we can monitor the performance in terms of parameters like movement and temperature and rotations, things of that nature. Absolutely. So it depends which performance you're talking about, but all of the parameters, I guess, that we discussed today, movements, rotations, the fundamental, even a little bit of wear data, that's a little bit more difficult maybe, but the point is that many of the main parameters of a bearing can be monitored even on an old bridge. It's not, doesn't have to be a new install.
Right. Okay, another question from Mr. Vidyut Kumar Rai. After applying full span load on spherical bearing, height of spherical bearing vertical dimension reduced by 5 to 6 mm. What is the reason behind it? I can tell that this should not happen, 5 to 6 millimeter reduction of height, because as we discussed in our slides, that spherical bearing, there is no compressible element at all. It's entirely made out of steel, only some sliding interfaces. So there must have been some gaps which were not, so during the assembly it was not filled in properly or something. It's very unusual. Daniel, can you put some light maybe?
Yeah, I agree. Normally, 1 or 2 millimeters, something maybe in this range would be considered normal. Exactly as Chinmoy said, I would suspect a settlement of other surrounding parts that maybe, the core of the spherical bearing should not certainly be compressing that much. But that question is difficult to answer. There's a lot of factors. But yeah, typically we would look for many fewer millimeters than that, I would say.
Okay, so next question is from Mr. Sandesh Kumar N. How to replace hinge bearings after some years in balance cantilever structure? Maybe Meghna, would you like to answer that?
I'm sorry, I could not hear the question. Could you please repeat?
How to replace hinge bearing after some years in balanced cantilever structure?
Oh, okay. So replacement is a big task when it comes to central hinge bearings, especially. So it would be better to have some kind of a solution which does not warrant the replacement during the lifespan of the bridge itself. So it would be better to go for some kind of a lift control mechanism which could help you keep the bearings in its pre-compressed state. That would be ideal.
Yeah, even if replacement is required, this basic male and female part that is attached to the structure would remain the same unless it has become loose from the structure. If the anchorages and have given away, that is a different thing. But if the anchorages are intact, the male and female parts are heavy steel construction, so there should not be any problem other than the corrosion. So that can be addressed in situ. The actual element, that is the rotating element, there are two pot bearings in top and bottom of the male part, can be externally replaced from outside. So there are some arrangements, the detail that is adopted by mageba, some arrangements by where you can take out those pot bearings, and if required, you can put a new bearing inside. That is possible.
Sure, because most of them are bolted connections. I think replacement would be is possible, of course. Yeah.
So question to Meghna from Alokda again. You showed Tejpur Bridge CHB. I am happy to see these scenes. We are the designer for this bridge. Yes, Mr. Homik, you are the designer of the bridge. My question is, which is better, needle beam option or hinge bearing as used in Tejpur Bridge? Yeah, okay. So needle beam application. Okay. I'd like to answer. Meghna, would you go for it?
Yeah, I mean, my answer would be it is at the end of the day a designer's choice, but a central hinge bearing sort of eliminates a lot of, I think, construction difficulties that could be associated with inserting of needle beam into the casing, etc. So that would be a preference, of course. But Alok,
yeah, also
that would be my
needle beam application is more prevalent in extra dose bridges. Of course, there is also a central hinge system there, but for normal concrete balance cantilever bridges, central hinge bearing, I see from the design perspective, it would be maybe as a better option, slightly. Okay, next question is Mr. Kunpang. Xiao Kunpang, I can explain how this bearing replacement normally carried out. Okay, bearing replacement, bearings are detailed to be in such a way that it can be replaced. So it is connected to the structure either by means of dowels. So where the bearings are then bolted. So if you release the load on the top from the top of the bearing just by jacking up the structure a little bit, just to release the load, then you can unfasten the bolts and take out the bolts, and the bearing can be then taken out horizontally very easily. Maybe in some future webinar we'll address this issue of bearing replacement for bridges, where we have some nice example of replacement projects that we have carried out. Yes, that can be future webinars topic. Okay, what is the benefit of the? Question is from Mr. John Senior. What is the benefit of POM seals over the brass ring? Mr. Ghosh, personally, I've never had an issue with brass ring. Yeah, it's a good question, Mr. Senior. But if you look at even our standards, codes and standards, it actually depends on the number of rotational cycles that this sealing ring can take. As per the standards provided, the POM sealing rings are at least twice, have the capability of taking the rotational cycles at least twice that of brass sealing ring. Yeah. So, but for normal road bridges, if you have correctly produced pot bearing with brass cylindering can survive, not a problem at all. But where rotational demand is much more, I would go for a pump cylindering. Daniel, does that answer the question correctly?
Yeah, I would say the exact same thing. There's a material difference there, and the brass rings are certainly functional, no question. We would just look to that the palm material to have a little better performance over the brass rings. I think there's maybe some constructability in there too that comes into it. I'm not an expert on that comparison, but I've at least heard that the palm rings being integrated into the disc the way they are is a bit of an improvement over stacking the brass on top of the disc. You have a little bit of tolerancing issues and things that come into the brass ring that do not come into the palm when integrated into the disc. Yeah. So.
Yeah, that's a good point. Another question from Professor Bandyopadhyay, that the static, dynamic, and fatigue response of a bridge also depend. Static, dynamic, and fatigue response of a bridge also depend on the performance of these bearings. Thus, monitoring of bearings seems to be an integral part of this HM. Please discuss. Yeah, of course, sir. We had a webinar last time where we actually addressed this issue that bearings can and should be equipped with structural health monitoring features so that we can address these issues. We can get the actual loads and forces and data like that, which can give the feedback to the bridge engineer about the parameters that he's interested in. Okay, why is this bearing not recognized by IRC or MRTH? It is a question from Mr. Selvan. I think the speaker, I thank the speakers and the moderator for an excellent. Okay, thank you, sir. It was very informative and educative. Thank you, all of that. So to answer the last question from Mr. Selvan, disc bearings, why it is not recognized by IRC or MRTH? See, these are, as Daniel in his part of the presentation addressed the issue, that disc bearing was originated in the United States. There is the major application in the United States. So it's more popular than any other type of bearings in US. Whereas in Europe, pot bearing and spherical bearings are more prevalent. Maybe traditionally we have followed the European style a little bit. So pot bearings and spherical bearings have been introduced. Still, you will find the spherical bearing code came out only in the year 2014. So it's not a very old code. So maybe there in this subsequent IRC publication, the disc bearing should also be addressed. Disc bearing has been is in use in India for a long time now. The first application, if I'm not wrong, is the Bandra Sea Bridge, where the entire bridge is is supported on disc bearings. It's a major iconic bridge. Second, Vivekananda Bridge, as Meghna showed in that slide, is also equipped with disc bearing. So it is in use for quite some time in India. So as you correctly pointed out, Mr. Selvan, that it's high time IRC stroke MORTH takes into account this very popular bearing and introduce it in their standard. Okay.
From the American perspective, I can say that the opposite is true in certain states. They have statewide qualifications for bearings, and they want disc and they don't want spherical, for example, and so it won't be recognized by a given state organization simply because they don't know it as well. And I think it's the same all over the world. These things have to be a little bit marketed, I guess. So.
Yeah. One last comment from Mr. Bhomik. As Daniel said correctly, bearings are like the knee of the bearing. I wish to add for bridges, heart is in the knee. Yeah. Of course. Yes. Of course, bearing is so important for bridges. It's very important for everybody connected with bridge engineering to understand the importance of the bridges. particularly the construction companies who are involved, should not, compromise. I don't say intentionally, but even unintentionally compromise on the bearing just because of the cost, because it is such an important feature of the only moving part, you can say. Bearings and expansion joints are the only moving part of the structure, so it should be taken care of with the greatest importance. Thank you, everybody. Thanks, Olokda, for your nice comments. So we come to an end to the question and answer session. So yeah, if we go to the next slide, maybe just